Welcome to lesson 16 of topology. In this lesson, I'm going to talk about continuous functions in topological spaces, or should I say between topological spaces. We have two definitions on this slide. One is continuity at a point, and then the other definition we're going to look at first is just continuity in general for a function. But then in the slide after this, I'll relate the two concepts: continuity at a point, in general continuity of a function over a topological space. A function f from a topological space x to a topological space y is continuous if the inverse mapping f of v is open in x whenever v is open in y. The idea is to capture the intuition that there are no jumps or separations in the function. So notice here we're using open sets to define continuity. If you recall from our metric space lessons on continuity, we had multiple equivalent definitions, and one of them did involve open sets, which looks exactly like what we have here. We also have continuity at a point. So again, we have a function from a topological space x to a topological space y, and it's continuous at a point x if for every open set v and y, such that f of x is an element of v, so here, there exists an open set u and x such that x is an element of u, and then f maps u into v. So quite a mouthful here. Let's kind of maybe look at the picture a little bit. So we're talking about continuity here at this point x. And it's saying that for every open set v that contains f of x, there's another set u in x, so that when you map it, your function f mapping u, in other words, the image of u under f, is this dotted line here, and that's inside of v. Okay, so a little bit of complexity here, but again, we're not using any distances. We don't have distances in topological spaces, so we have to use this open set basis for defining continuity. And the idea is that you have your set x here, and you can kind of squeeze it a neighborhood around f of x is as tight as you need based on any open set in your function, your topological space y. We have the theorem on this slide that I mentioned on the previous slide. Let x and y be topological spaces. A function f that maps from x to y is continuous if and only if f is continuous at each point of x. So we're going to prove this in both directions. Let's start with this direction here. Assume that f is continuous at each point of x. Take any open set v and y. So this is, let's say this is y on the right side of the screen down here. We take any v, any set v and y, and take any x that's in the inverse of v. So the inverse f inverse of v is a set in x. So we'll take any x in f inverse v. So we've drawn that here. By definition of continuity at a point, there exists an open set u sub x that contains x such that f evaluating all the points at u sub x is a subset of v. So here's our u sub x. It's surrounding x. X is an element of u sub x. And then if we map this via f, we get f u sub x, and that's inside of v. So that follows from the definition of continuity at x, which implies that if we take the inverse on both sides of this, then we have that u sub x is a subset of f inverse of v. So we can draw this completely inside of the f inverse of v. Okay, so we do that for each x in our f inverse v. We do this u sub x. So we take the union of all these u sub x. So for each x in here, we're going to get a different u sub x. That's what this notation here is. For each x in f inverse v, take the union of these u sub x sets. We'll let that equal u. Being a union of open sets, u is open, we know that. Any union of open sets in a topological space is open. So u, which I haven't drawn in here, but it would, we want to show it's actually equal to f inverse of v, but let's just say it's surrounding all these u sub x terms. In addition, f evaluated at u is a subset of v, and that's because if we take f evaluated at u here, then distribute that over all these unions, each one of these is in v, so the union of them all is in v. So f evaluated at u is inside of v. I didn't draw it, but it would be just inside of this v here. And then we take the inverse on both sides of this, and that implies u is a subset of f inverse of v. So u is inside of here, inside of this line this region. And since u contains every point of f inverse v, that's how we defined it here, we have that f inverse v is a subset of u. So we have u is a subset of f inverse of v, and f inverse of v is a subset of u. And so the only conclusion is f inverse v equals u, which is what I mentioned. That's what we want to show. And finally, f minus v being open implies f is continuous. So that we basically have shown the proof of this theorem going in the backwards direction, so to speak. If you're continuous at every point in x, then f satisfies the definition of continuity as a function. Okay, so now we need to go in the other direction, and I'll show that on the next slide. We need to prove the theorem in the other direction, so let's assume f is continuous, then show it's continuous at each point. So we'll take any x in the domain, so that I've drawn it down here. This side is x, and this is what's being mapped to as y. Just trying to save a little space, so I didn't draw an x and y here. But let x be an element of x, and v be an open set containing f of x. So we map x to f of x using our function, and then we're saying let v be any open set that contains f of x. In other words, f of x is an element of v. Then the set u equals the inverse of v here is open, since v is open and f is continuous. That follows from the definition of continuous function, which I've copied down here. Further, since x is an element of u, that's just the way we defined it, and this is a property of functions, f of u is a subset of v, so the f applied to u is a subset of v, so I've drawn it in here, and thus f is continuous at x. That's just a statement of the definition of continuity of a function at x, which I copied down here at the bottom for you to, so you didn't have to turn back to the definition on the previous slide. Okay, so we've proven that in both directions. I think as I mentioned when we started, I think it's kind of obvious, or at least something you'd hope to be true, that if a function is continuous in general on a topological space X, then it's continuous at every point. And if it's continuous at every point in X, then the function follows the definition of being continuous over the topological space X. Given two functions, f that maps from X to Y and g that maps from Y to Z, where X, Y, and Z are topological spaces, we can define a third function known as the composition of functions. The composition of g with f at X is written g of f of X, or sometimes this notation here. This is a little more explicit because it's emphasizing that you evaluate f at X, and then whatever the output is, which would be in Y, then g takes that and maps it to Z. So g of f maps from X, your initial input, and then you eventually end up with an element in Z. Now, if you want to go in the other direction, f of g, this here, that can be possible, but keep in mind, if you're doing f of g of X, then g maps from Y to Z. So whatever you map to in Z would have to have some overlap with X in order for f to be able to map it to Y. So that's why I'm saying the intersection of X and Z. They don't have to be equal, but they at least have to have a non-empty intersection, so that when you map from Y to Z, you get something in X that you can work with, f meaning f can work with, that maps it to Y. So let's look at a few examples here. Take an easy one where X equals Y equals Z, and they're all equal to the real numbers. So this is maybe something you've seen in pre-calculus or calculus. So let f of X equal X squared, and g of X equals X e to the X. So f of g of X, this thing here, you put in, for instead of X, you put in g of X. Then you evaluate f at g of X, which is e to the X. And so you put e to the X into this, which would be this e to the X squared, and that gives you e to the 2X. Now, if you go in the other direction, it is possible because these are all equal, so we can do this. We evaluate g at f of X. So we have to put X squared into X, which is what we do here, and we get e to the X squared. So you can see these two are not the same, and that's usually the case. The inverse function of a composition, assuming both functions are invertible, has the property that the inverse of f of g equals g inverse of f of inverse. So I don't prove it here. This is something that's kind of outside of the scope of the lesson, but for a proof, you can have a look at section 4.3, page 362 of the book by Rogers. This is reference 83 in my book, which you can download freely. I know I've mentioned that several times. And I believe this book is available on the Internet Archive, so you can borrow it for like an hour at a time, I believe, if you're really interested in this. But the main point I want to get here is just that I may need to use this later on, and I didn't want to just kind of throw it at you without at least giving you a reference and at least mentioning as a reminder. You've probably seen this before in calculus, but I thought I'd put it here just as a reminder. Theorem 99 concerns the composition of functions. If we have function f from X to Y and g from Y to Z, and both of these functions are continuous, and X, Y, and Z are topological spaces, then g of f is continuous. The proof is pretty simple using our definition of continuity. Take any open set V and Z. Since g is continuous, g inverse of V is open in Y. And since f is continuous, f inverse of g inverse of V is open in X. And this quantity here is basically G of F inverse. And so that proves that G of F is continuous. So this is a simple proof compared to the epsilon delta type of proof that we saw when we proved this similar theorem for metric spaces. So here we have an advantage of having a more abstract structure, such as a topological space. In this case, we actually got a simpler proof. And not only that, but it applies to metric spaces and anything else that happens to be a topological space. We have something called a homeomorphism between topological spaces, and it's defined to be a bijection. That means one-to-one. So if you have two topological spaces, every point in X gets mapped to a point in Y, and the inverse of every point in Y gets mapped to X. And onto means that X doesn't get mapped to just the subset of Y, but in all of Y. So everything in Y gets mapped back to something in X. So that's one-to-one and onto. That's called a bijection. And so a homeomorphism is a bijection that is continuous and whose inverse is also continuous. From the standpoint of topology, homeomorphic topological spaces, to be particular, are essentially identical. A characteristic of a topological space qualifies as a topological property if it remains unchanged under homeomorphisms. I have a couple examples of that here. So discreteness, in other words, if you're just a finite set or a countable set, exemplifies a topological property. If two spaces X and Y are homeomorphic, X is discrete if and only if Y is discrete. That would kind of make sense to me on the surface. Metrizability also constitutes a topological property. However, attributes tied to particular metrics usually fall outside of this category. Broadly speaking, any property discernible in relation to open or closed subsets of a space qualify as a topological property, and then would be preserved via homeomorphism. So I have a simple example here. Take two intervals A, B, and C, D in the real numbers, and these are sub spaces. A, B is a subspace of R, and C, D is also. And as I mentioned here, so if we consider this function f of x, we have a constant here which looks kind of menacing, but we'll explain that in a second. So this constant times x minus a plus c, consider that function. F is continuous. We can see that here, it's continuous, and it's just a line segment. If we took this restriction off, then it would just be a straight line. So we know it's continuous. If you put in f of a, this drops off to 0 and you just get c. So you can see a gets mapped to c. And if you put in if you put b in for f, then you get b minus a here. That cancels with this b minus a, and you get d minus c plus c, and you get d. So you maps here, and then everything in between maps to the internally to C. I didn't prove that, but everything in between maps internally between C and D. That's what I mentioned here. So we have a homeomorphism. It's a bijection. It's continuous. Its inverse is continuous. And so the two subspaces, A, B, and C, D, are homeomorphic, which shouldn't be a surprise. You may want to just think about it for a second. They don't have to be the same size. So AB could be from 0 to 1, and CD could be from minus 5 billion to plus 10 trillion. You know, it could be a huge interval, but yet they're still homeomorphic. And some of this goes back to the cardinalities of infinite sets. And all open intervals have the same cardinality in the real numbers. And it's something we're not going to get into in this particular set of lessons, but I'll just mention it here for completeness. Okay, so that's the end of this lesson. We'll have a few more on topology, and please stay tuned.